Hello, my name is Samuel Weiss-Cowie, and today I'll be talking about Lab 5 from Physics 2212. Here's a brief overview of today's presentation. The lab goals were to observe the behavior of a magnet dropped through a roll of aluminum foil and then create a computational model to mimic the observed behavior. It was found that the computational model predicted a longer fall time than what was observed in the experiment itself. Some key concepts for this lab include Faraday's law, pictured here, magnetic flux, pictured here, the Biot-Savart law for a magnetic dipole, which is here, and Newton's second and third laws. Here's a version of Newton's second law. Newton's third law simply has to do with equal and opposite forces. The experiment itself first involved determining the direction of a bar magnet's dipole moment using a magnetometer app, and then dropping the magnet north side down through a roll of aluminum foil while recording the procedure with a phone camera. This was repeated for a total of 5 trials, after which point the videos were used to determine the duration of the magnet's passage through the tube. Here are some answers to the checkpoint questions. First, we had to use a non-ferrous material, because otherwise the magnet would stick to the inside of the tube and not fall through the bottom. Second, the magnet took longer to fall through the tube than would be expected, absent simply gravitational and air resistance forces. This can be seen by using the kinematic equations, which would predict a fall time of 0.178 seconds through a tube of length 0.31 meters, which is much less than the observed time of 1.93 seconds. Here are measurements from the experiment for the 5 trials and the average fall time. Now for the experimental model, we will be using Faraday's law to explain the behavior of the magnet. So, the magnet's dipole moment is directed downwards. Therefore, as the magnet falls, downward flux increases through the tube. And therefore, a current is created in the tube to counter the change in flux, as described by Lenz's law. The induced current then generates a magnetic field that exerts an upward force on the magnet, which is able to counteract some portion of the gravitational force, thereby slowing the magnet's progress through the tube, or at the very least decreasing its acceleration. Now for the code, on lines 34 to 37, I changed the tube's parameters to match the aluminum foil tube I used. Lines 71 to 72, I modified the magnet's parameters to match my magnet, with mu calculated during lab 3. Lines 97 to 102, I create a function to calculate magnetic field from the bar magnet at a distance r. Then on lines 115 to 122, I have an equation for calculating the change in flux. Then on lines 132 to 146, we initialize the loop that will run the simulation for a number of rings in the tube. On line 156, we calculate the change in flux for a given ring. Then on line 174, we calculate the magnetic field at that same ring. And on line 176, we calculate the sine of the angle between the ring's radius and the bar's magnetic field, which will then be important for our magnetic force calculation, which occurs on line 177. And then the remaining lines through line 186 involve other force calculations. Lines 191 to 192, we update the bar's velocity and position based on the concept of momentum. While the bar magnet fell through the tube, I saw the tube turned red, indicating the red corresponds to a counterclockwise current, because that is what would create an upward magnetic field from the induced current. The magnet behaved the exact same when it was oriented the opposite way. The real-world magnet fell more quickly through the tube than the code's magnet. This is the difference in time. And the accuracy could be improved by increasing the ring number or finding a more accurate mu value. The magnetic and gravitational forces are nearly equal while the magnet is in the tube, which is shown by the fact that velocity barely changes while the magnet is in the tube. And this is explained by Newton's second law, where net force equals 0. With negligible tube resistance, the bar magnet would likely get pushed back out the top of the tube, because lower resistance means a higher induced current. Higher induced current means a larger magnetic field, and a larger magnetic field means a larger magnetic force pushing upwards on the bar magnet. And depending on where holes were cut in the tube, the magnet might drift to one side. The holes are just on one side of the tube, or the magnet may not be affected if they are evenly spaced along the tube, like in a solenoid.